So this is the integral curve. Hey, wait a minute, it's not tangent to the line element there, it didn't even touch it. Well, I can't fill up the plane with line elements. Here, at this point, there was a line element, which I didn't bother drawing in, and it was tangent to that. Same thing over here, if I drew the line element here, I would find that the curve had exactly the right slope there. So, so the point is, the integral, what distinguishes the integral curve is that everywhere it has the direction, that's the way I'll indicate that it's tangent, has the direction of the field everywhere at all points. At all points on the curve, of course. Where it doesn't go, it doesn't have any mission to fulfill. Now, I say that this integral curve is the graph of the solution to the differential equation. In other words, the differential, writing down analytically the differential equation is the same geometrically as drawing this direction field, and solving analytically for a solution of the differential equation is the same thing as geometrically drawing an integral curve. So what am I saying? I say that in integral curves, all right, let me write it this way. I'll make a little theorem out of it. That y1 of x is a solution to the differential equation if and only if the graph, the curve associated with this, the graph of y1 of x is an integral curve. Integral curve of what? Well, of the direction field associated with that equation. But there isn't quite enough room to write that on the board, but you can put it in your notes if you take notes. So this is the relation between the two. The integral curves are the graphs of solutions. Now, why is that so? Well, in fact, all I have to do to prove this, if you can call it a proof at all, is simply to translate what each side really means. What does it really mean to say that a given function is a solution to the differential equation? Well, it means that if you plug it into the differential equation, it satisfies it. Okay, what is that? So how do I plug it into the differential equation and check that it satisfies it? Well, doing it in the abstract, I first calculate its derivative, and then how will it look after I plugged it into the differential equation? Well, I don't do anything to the x, but wherever I see y, I plug in this particular function. So in notation, that would be written this way. So for this to be a solution means this. That equation is satisfied. Okay, what does it mean for the graph to be an integral curve? Well, it means that at each point the slope of this curve, it means that the slope of y1 of x should be at each point x1, y1, it should be equal to the slope of the direction field at that point. And then what is the slope of the direction field at that point? Well, it is f of that particular, at the point x, y1 of x. If you like, you can put a subscript 1 on this and a 1 here or a 0 there to indicate that you mean a particular point, but it looks better if you don't. But there's some possibility of confusion, I admit to that. So the slope of the direction field, what is that slope? Well, by the way I calculated the direction field, its slope at the point was to be x, whatever the value of x was, and whatever the value of y1 of x was, substituted into the right-hand side of the equation. So what the slope of this function, of that curve, should be, of the graph, should be equal to the slope of the direction field. Now, what does this say? Well, what's the slope of y1 of x? That's y1 prime of x. That's from the first day of 1801. Calculus. What's the slope of the direction field? This? Well, it's this. And that's what the right-hand side. So saying these two guys are the same, are equal, is exactly analytically the same as saying these two guys are equal. So in other words, the proof consists of what does this really mean? What does this really mean? And after you see what both really mean, you say, yeah, they're the same. So I don't know how to write that. It's okay. Same. How's that? This is the same as that. Okay. Well, this leaves us, the interesting question is, how do you draw a direction field? Well, this being 2003, mostly computers draw them for you. Nonetheless, you do have to know a certain amount. I've given you a couple of exercises where you have to draw the direction field yourself. This is so you get a feeling for it, and also because humans don't draw direction fields the same way computers do. So let's first of all, how do computers do it? They are very stupid. There's no problem. Since they go very fast and have unlimited amounts of energy to waste, the computer method is the naive one. You pick the point, you pick a point, and they're usually equally spaced. You determine some spacing. This point, that one, blah, 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 blah. Equally spaced. And at each point, it computes f of xy at the point. Finds means it computes the value of f of xy, that function. And the next thing is, on the screen, it draws at xy the little line element having slope f of xy. In other words, it does what the differential equation tells it to do, and the only thing that it does is if you're telling the thing to draw the direction field, about the only option you have is telling what the spacing should be. And sometimes people don't like to see a whole line. They only like to see a little bit of a half line. And you can sometimes tell, according to the program, tell the computer how long you want that line to be. If you want it teeny or a little bigger. And once in a while you want an arrow on it, but not right now. Okay, that's what a computer does. Now, what does a human do?